Welcome to part 2 of chapter 19. Now we're going to talk about a couple of different things. One, we're going to talk about electric field lines, kind of what they look like, and then look at equipotential lines within that. All right, so if we look at a point charge, we have the force due to a point charge, our 2 point charges, Q1, Q2 over R squared, and we normalize that to get the electric field down to one charge, get the force per unit charge, then it's just KQ over R squared. Well, that just radiates out directly from a charge Q, just like these little arrows are showing here, right? So R hat just points away from Q. If Q is negative, all that does is reverse the arrows in all of this, right? And they just point the other way. So if we look at this, and we look at these circles, right? All around these circles, we're not moving against, if we move around this circle, we're not moving against the electric field at all. That means we're at the same potential energy, right? Our potential energy isn't changing a bit as we go around this circle. It's kind of like if this were gravity and this were the Earth in the middle, and you're going in a big circular orbit around the Earth, your gravitational potential energy isn't changing at all because your height isn't changing. You're at the same height above the Earth the whole time, right? So we can actually move a charge Q along these circles and not experience any force on it. So these are what we just call equipotential lines, all right? And the electric field, the magnetic electric field is perpendicular to these circles, or this is actually a sphere, right? If you think in 3 dimensions, this is a sphere. And the potential is just given by the voltage, the potential is KQ over R. So electric potential goes down as 1 over R, right? Go back. The electric field goes down as 1 over R squared, right? Electric potential 1 over R. The work done moving a charge along one of the potential lines is just 0 because electric field is perpendicular to it all. All right. If we begin to try and imagine what does the electric field and what do equipotential lines look like for other charges, well, here are a couple of different scenarios. Here's a plus charge and a minus charge. And remember, the electric field goes from plus to minus, so you end up with these shapes like this, and these lines go way, oh, sorry about that. These lines go way out and back in, and until you get to this line that goes straight out, goes all the way to infinity and can be imagined to then wrap back around and come in from the other way. And then right here in between them, all of these lines are perpendicular to that line, that vertical line right there. All these lines come in, they're perpendicular to it. That's actually an equipotential point. Everything's perpendicular to it right there. And these other little squashed circles are also equipotential lines in this picture where they cross the electric field. They're always crossing the electric field lines in a way that they are perpendicular to the electric field. Down here in this graph, right, we're looking at two charges that are both negative. So the lines point into both of these charges. Well, they're not going from one to the other, right? They're all coming in from infinity. So you get these lines coming in from infinity from all over the place. There's a big equipotential surface out here that encircles them all. Move a little closer. There's another one, right? And then when you start getting close enough, you start getting to where, oh, there's one that just wraps around here, one that just wraps around here, right? So you've got these equipotential lines as you get close to one of the charges. So you've got kind of like islands here, right? Wrapped around these two charges. All right, that's it for equipotential lines. The big things, the big takeaways from this are electric field due to a point charge equals KQ over R squared gives rise to an electric potential due to a point charge, which is KQ over R. And this R is nothing other than distance you are, the distance you happen to be from the charge Q. All right, that's it for this segment.